Aloha. My name is Roger Jelinek. I'm Executive Director of the Hawaii Book and Music Festival. And it's my great pleasure to welcome the attendees and also this really spectacular panel on the question that's on everybody's mind here in Hawaii, which is why do we need both ground and space telescopes? That is on everybody's mind who doesn't know what they're talking about, basically. Anyway, without further ado, I'm going to turn this over to astronomer Roy Gao of the Institute of Astronomy. So take it away, Roy.
Okay, aloha kako, and welcome to this evening's talk. Thank you to the Hawaii Book and Music Festival for hosting us and for allowing us to have this panel discussion here. So as Roger said, we're going to be discussing why do we need both ground and space-based telescopes. And I'll be the moderator for today and providing an introduction. I'm joined by John O'Meara, who is at Keck Observatory, and Tom Greene, who's at NASA Ames. And I'll give you a little bit more biography of them in just a second. But before I do, I wanted to share that in case you don't know, on the evening of November 7th, we will be treated to a lunar eclipse, which you are all welcome to go outside and enjoy with your naked eye or with binoculars. It's a total eclipse here in Hawaii, so let's hope for good weather. But in case you'd like to see what it might look like through a telescope and you don't have one, you can join our live stream at the Institute for Astronomy's YouTube channel, which you see on the screen there. And we'll start streaming about 11 p.m. on Monday night and keep going till about 2 in the morning on Tuesday. So go out and enjoy this great celestial sight. So as I said, I'm joined by John O'Meara, who is the Chief Scientist and Deputy Director at the Keck Observatory on Hawaii Island, Mauna Kea, the headquarters in Waimea. He received his PhD in physics from the University of California at San Diego, and he was an astronomy professor at Penn State and St. Michael's College before heading to Keck. He's served on many national committees and mission teams, so he's experienced with both ground and space-based observatories. And he is currently the chair of the National Science Foundation's Astronomy and Astrophysics Advisory Committee. So he has a lot of insight both into the observatory operations, ground-based telescopes, and the whole picture of astronomy in the United States. In addition, we have Tom Greene, who received his PhD in astronomy from the University of Arizona in 1991 and is now an astrophysicist at NASA's Ames Research Center. He was a staff scientist at Lockheed Martin, and he was for some time here in Hawaii as a member of the faculty at the University of Hawaii and the staff of NASA's Infrared Telescope Facility, which is on Mauna Kea. And he's a co-investigator on 2 of James Webb Space Telescope's science instruments. So he's deeply familiar with JWST and other space missions. And I'm Roy. I got my PhD in 2001, and I've done postdoctoral work at Johns Hopkins and UC Davis. And I'm currently an astronomer at the Institute for Astronomy, and I coordinate our public outreach events and do our press releases and things like that. So I'd like to say, if you have any questions, what we're going to do is we'll keep an eye out for questions after everyone's spoken, and we'll also have an internal conversation. If you all don't join and ask us questions, then we'll ask each other questions on the panel. So I'm going to give a little bit of broad background on why we have many different kinds of telescopes on the ground and in space. And I think a good analogy for why we have different telescopes is thinking about the idea that we have many tools for many about the transportation sector. You want to go someplace. Well, if you want to go to California, you need an airplane from Hawaii. You might want to travel to an island, and then you'll need a smaller airplane. Maybe you need to carry some big cargo. You need a different kind of airplane. But going up in the sky isn't the only way to go. You might need a boat. Or maybe you've got the hottest new vehicle, maybe a fancy Tesla on the block, but that's not going to serve all the purposes you need. Maybe you need a pickup truck to carry something, or even a bigger van. Or you want to carry a lot of people, so you need a train. And even among all the trains, there's different kinds. So if we just think about astronomy as travel, then we need different kinds of tools to do different kinds of astronomy. And that's exactly why we have different kinds of telescopes. And here's an example of the diversity of telescopes that we have. And I'm going to talk about why some of them look different than what they do. But we have telescopes up on Mauna Kea, large ground-based telescopes with apertures of 10 meters or 30 feet across. We have smaller ground-based telescopes like Atlas, which is only 3 feet across, but surveys the sky looking for asteroids. We have giant radio telescopes like the Green Bank telescope. That might not look so big to you, but that dish is the size of a football field. So it's like a football field up in the air that we can rotate and turn around and move. And we have space-based observatories that look at all kinds of different wavelengths of light and do different kinds of jobs. So just like we have lots of different vehicles, we have lots of different kinds of telescopes. And one of the reasons that we have those many different telescopes is that we want to look at light of many different colors or many different wavelengths. What we perceive with our eyes as human beings is what we call visible or optical light, and you can see that in the rainbow in the middle of this picture. But there's light that's at longer wavelengths, at colors that we don't see, such as infrared and radio waves. Radio waves are how our cell phones communicate with each other, for instance. And those wavelengths of light we're not sensitive to, but we can build telescopes that are sensitive to them. There's also shorter wavelengths of light, higher energy light, like ultraviolet, which we all put on sunscreen to avoid getting burned, or X-rays, which if you had an injury, you might have gotten an X-ray, and even gamma rays that turn you into the Hulk if you're bombarded by them. But you'll also see from this diagram that many of those colors of light, which many different kinds of astrophysical objects give off, don't make it to the surface of the Earth. So while we can build telescopes on the ground, as you can see in the green here, that's the ground level. If we want to see objects that give off only X-rays, objects that have very high energy light, we need to go above the atmosphere. And that means going to space, or in some cases, balloons or airplanes. So you can already see that there's some things we can do from the ground and some things that we cannot. So that's already a reason for going to space, but also a reason for being on the ground. And those different colors of light that we want to see tell us about different things that are going on. Here's pictures of the Whirlpool galaxy in different colors of light, going from the longest wavelength radio light to the highest energy gamma rays. And you can see that each color of light highlights some different feature of the galaxy. And I'm not going to go through all of the science that you can do, but if you want to really understand what's going on, you need to look and see what all the different components of something out in space are and what the different physics are that's going on. And for that, you need the different colors of light. And we also make telescopes in different sizes, just like we make airplanes and cars and trains in different sizes. And there's two reasons for that, two main reasons. First, a larger telescope collects more light. And I put a picture here, not of telescopes, but of solar panels. I don't know how many of you have solar panels on your house. I do. But as you know, the more solar panels you have, the more sunlight you collect and the more power you get. So that gentleman with the small panel in his hand is not going to collect a lot of sunlight, whereas that big panel farm is going to collect a lot. And whether it's sunlight or starlight from distant stars and galaxies, the bigger we make our telescope, the more light we get, so the more faint objects we can see. And how much light you collect depends on the surface area of your telescope. So that goes as the radius squared. The other thing that people don't appreciate so much usually is that the bigger you make your telescope, the more resolution, the more detail you can see. So if you were looking, let's say, in visible wavelengths of light, and you had Hubble Space Telescope and you took, whose diameter is 2.4 meters or about 7 feet or 8 feet across, and you took a picture of this cluster of stars, it would look blurry and you couldn't tell what's there exactly. A telescope like an 8-meter telescope, something like, sort of a little bigger than James Webb, or in this case, the Gemini Observatory on the ground, but with adaptive optics to correct for the blurring from the atmosphere, you can immediately see more detail. But still, you see there's a lot of blurring going on. You can't quite tell what's going on in the middle of this star cluster. And if you made a 30-meter class telescope, even here on the ground, and corrected for the atmosphere, you could see many more individual stars and make much more precise measurements. So for being able to see faint and for being able to see detail, you need telescope size. Size isn't always what you want, but it often is. And you want to see different size scales in objects because, for instance, in a galaxy, you might want to take a picture of the whole galaxy, or you might, as in this picture, want to see the black hole at the very center of the galaxy. And that donut-shaped circle at the bottom is the famous image of Poveghi, the black hole in the center of M87, where we combine light from telescopes all across the Earth to get so much detail, so much resolution, that it's like having a telescope as big as the Earth. So we can get incredibly high resolution, but you can see if all we had was that high resolution, we could not see these jets of material shooting out of the black hole and being launched into space. And then if we went even further out, we'd see the whole structure of the galaxy. So we want to be able to understand things on different size scales, just as your doctor might want to take a biopsy of something and see things on the cellular level, but also want to take a look at your whole body. And finally, I want to say that we don't just want to see things in detail or take pictures at different image sizes. Sometimes we want to really have telescopes with completely different purposes, from mapping the sky, so telescopes with giant cameras with wide fields of view, kind of like taking a panoramic photo with your cell phone. And that can be a small or even a big telescope with an enormous camera, but those will never see fine detail. Their job is to map the whole sky. Or you might have telescopes with smaller fields of view, like many large telescopes, but not all. And those will study individual objects that we find in great detail. So you can see that we have lots of reasons for having lots of different kinds of telescopes. And I'm going to leave it at that, and I'll let John take over to tell us about more detail about ground-based telescopes and what they have to offer and some of their pros and cons.
Right, thanks very much, Roy, for teeing that off so very well. And aloha, everybody. Thank you for joining me, and thanks to the Hawaii Book and Music Festival for inviting us here. It's great to work with everybody here. Hopefully, I can get the screen share to work not too badly. Do we have it correct? All right. So the first thing is a little bit of shameless promotion. On November 1st, on the night of November 1st, Keck Observatory is having another one of its online public talks. And we're really happy to have Dan Huber from the University of Hawaii talking about how to understand sound from inside stars. And I don't want to give away what he's talking about, but it's very exciting. We're really lucky to have Dan. So if you go to keckobservatory.org and click on Cosmic Events, it's a free public lecture similar to this format. And we try to do those about once a month. Okay, so I've been asked to talk about ground-based telescopes. As Roger said at the beginning, I do both ground is, as Roy said at the beginning, I do both ground and space-based telescopes, but I'm the chief scientist here at the Keck Observatory, so I want to talk about ground-based. And so I really want to talk about how it started and how it's going. On the left is one of the first telescopes ever used to point up at the sky and write things down. That's Galileo's telescope from 1610. And on the right is an image of the facility that I'm the chief scientist for, the Keck Observatory. So these represent sort of the bookmarks of ground-based astronomy today, from the first and least powerful up to the current and most powerful today. And in many ways, the history of ground-based astronomy has been the quest for aperture. As Roy pointed out, the larger a telescope you get, the fainter objects you can see and the more detail in those objects you can see. So, at the beginning in 1610, you had Galileo's telescope, which had an entrance aperture, which was only about this big, a couple inches across. And it was a set of crude lenses on either end of a tube. It worked well enough for Galileo to have enough resolution to determine that Jupiter had moons, to determine that the moon's surface was not smooth, to determine that Venus had phases. And so even that change between your eyes and this much fundamentally transformed our understanding of the universe. But as time progressed, people realized that we wanted to have bigger and bigger telescopes. So in the late 1600s, Isaac Newton in 1688, for example, came up with the idea of, instead of using lenses, to use mirrors. And the reason being is that making a lens perfect is difficult because you have to make both sides of the thing perfect, whereas making a mirror perfect requires only one side. And as time marched on, 100 years later, Herschel created the first of the real giants on the sky, a telescope with about 4 feet in diameter, about half the size of Hubble's mirror in diameter. And people started to have to build facilities and decide where to put them instead of people's backyards. to really harness the power of large telescopes. And then it became an engineering problem, not just a desire to look at the sky, but how to build that instrument. And in Palomar, which was pointed out in 1949, the largest telescope in the world at the time was built with 5 meters in diameter, the 200-inch Great Eye at Palomar, which was really sort of the last of the massive telescopes that came out there. We've since had larger telescopes, but Palomar was effectively a battleship with a mirror attached to it. And then finally, to the modern day, the next great leap was the 8 to 10 meter class telescopes like Keck, which had its first light almost 30 years ago, which has a 10-meter diameter across. So the march of ground-based astronomy has been very intricately tied to the present day with the march for getting bigger and bigger things. And then looking forward, the next great era in ground-based astronomy is the true uber behemoths, the things that are 2 to 3 times the size and diameter of the Keck telescopes. But the gathering power of a telescope can go anywhere between the area, which is d squared, and the d to the 4th power. And so these are massive leaps forward in gathering power. And all of these telescopes are engineering marvels. What's behind these two gentlemen is the primary mirror before putting the coating on top of it of the Palomar telescope. And they had to figure out how to make something that was rigid enough to aim at different parts of the sky and not be floppy, not bend due to gravity. And this was actually the first use industrially of a material which we now call Pyrex, developed by Corningware to first try to solve this problem. And then they realized it's very rigid and stiff against both gravity and changes in temperature. So you could use it to bake things in your oven or to build big telescopes. But it took decades to get to the point where they could build something and actually aim this on the sky. So these are true engineering marvels. I think the Keck Observatory, Palomar, all of these things, Gemini, they're all amazing engineering marvels to work against gravity to keep these ultra precise machines tracking on the sky. So I want to speak to why go with the ground, because Tom is going to speak to why go with space, even though in the end, I'm willing to bet we both agree that we both need both hand in hand. The first is that on the ground, you have far fewer constraints on the size of the telescope that you can build. You have to launch space telescopes, which means you have to put them on a rocket. And rockets can only get so big, at least in the current day. And so you have very big constraints on how heavy your thing can be, how much power it can use, how much space it can take up. Tom will speak to the fact that Webb had to unfold. And you have none of those constraints on the ground. Your fundamental constraint is gravity and money on the ground in terms of how big you want to build them. You can fix ground-based telescopes whenever they break. So if something goes wrong with your instrument or your telescope, you send a crew of people up, they go and fix it. And this can happen on a daily basis, on an hourly basis. With space, you don't have that luxury. Only one space telescope has been serviced by human beings, the Hubble Space Telescope. Right? They can be upgraded. Right? Palomar is still doing cutting-edge science today. Keck is still doing cutting-edge science today. Most of the telescopes in the world that are there are still doing cutting edge science today because they can be continuously upgraded. You can change the technology there. And you can have a wider range of instrumentation. Keck has 10 instruments, right? Hubble has 4. James Webb has on the order of 4, right? They have different configurations, but we can constantly change the flavor of the instrumentation on the ground. And you have different flavor of operations, nimbleness, how quickly we can move from different things, how quickly we can change our mind. It is very expensive in terms of fuel and operations to change a space telescope. It's trivial to do it on the ground. We can incorporate new technologies faster. I believe Tom's going to speak to that. They're easier to coordinate across telescopes and to tell one set of telescopes to look at one thing and another. And finally, money, right? On average, a ground-based telescope is going to cost significantly less than a space-based telescope for a similar set of capabilities. And so that's why some of the advantages of ground-based telescopes, even though they have a fundamental disadvantage, which is that they're on the ground. They still have to look through the atmosphere, even if you put them in one of the most pristine sites on the planet, which is Mauna Kea. So here's an image of the summit of Mauna Kea from above at 14,000 feet. We put telescopes there because this is one of the absolute best places on the planet to do astronomy. The way that the air flows over the shield volcano of Mauna Kea, the altitude of the site, the constant temperature. We shouldn't have telescopes there unless they really have the best opportunity to take advantage of the science. And that's why we build telescopes there. And there are a number of telescopes at multiple wavelengths. The Keck telescope is there. I'm going to focus primarily on optical wavelength telescopes today. But as Roy said, we take advantage of as many parts of the electromagnetic spectrum as we can, because the stars don't care about what telescopes we build. They're making light at all those wavelengths. But Mauna Kea is absolutely one of the best places on the planet to do astronomy because of the atmospheric conditions and the altitude where they operate. A bit about Keck Observatory, right? Keck is a large enough telescope that you couldn't make it out of a single mirror, a single piece of glass. Instead, we use 36 segments that are merged together, kind of like a puzzle. And you can see that primary mirror here. When Tom talks about Webb, you'll see that it looks fairly similar. This is a segmented mirror telescope. And this is what it looks like from above. There's not one, but two of them, Keck 1 and Keck 2. Keck 1 came online in 93, Keck 2 in 96. And this is how it works, right? The light comes in from afar, bounces off of that primary mirror, can bounce back up off of the secondary mirror, and then can either go off of a tertiary mirror onto the side where instruments live, or down to the bottom of the telescope where other instruments live. And those instruments are not small. They're not like your iPhone camera, right? This is one of our instrument science manager, Mark Cassis, standing next to a big infrared instrument called MOSFIRE. And this is another instrument called KCWI. These are often very, very large, very complicated, very bespoke instruments. There's only one of these on the planet. And for reference, speaking to that advantage of the ground, that instrument weighs 2/3 of the mass of the entire James Webb Space Telescope. We can afford to put that much mass, power, and all that thing on the ground because we have a superstructure in the telescope system that can support it. We don't have to launch that thing. We only have to crane it, ideally once. We do have the problem that the sky blurs things. And to get around that, we use a technique that Roy spoke to called adaptive optics, where we basically create false stars on the sky, measure how much those stars don't look like a perfect dot on the sky, and try to quickly change our mirrors to get rid of the blurring of the atmosphere. And that's the process of adaptive optics, optics which can change hundreds of times a second. And that has extreme power. On the left of both of these frames is something that would happen if you didn't have that capability. And these are both Keck images. On the left is when you don't have adaptive optics on. And on the upper frames, it's the center of the Milky Way galaxy. On the bottom is the planet Neptune. And on the right is what happens when you turn that adaptive optics on. Right now, today, adaptive optics primarily works in infrared wavelengths of light, which is a huge advantage for space telescopes because they don't need adaptive optics at any wavelength of light. They don't have the atmosphere boring. And we have rapid response. Sometimes things go boom in the night and you have to follow them up within minutes or hours before they go away entirely. And so ground-based telescopes oftentimes have the advantage that they can very rapidly change their mind of what they're looking at, and they don't have to spend fuel to do it. They don't have to be worried about the angle relative to the sun or any of those things when they do it. And that's a key important thing. So I'll close with what's next. I think there are 4 big things to think about what's next. The first is the Rubin telescope, which is in the southern hemisphere. Rubin will image half the sky every night. It is a massive survey telescope. It'll be the largest camera, the largest view of the sky with every image that will be taken by any telescope anywhere. And it'll be a huge data mining experiment. This is when astronomy enters really into the era of big data. And also in Chile is the European Extremely Large Telescope. The European system has an unfortunate naming system of being literal. Right now they operate the Very Large Telescope, and this is now the Extremely Large Telescope. They had plans for the Overwhelmingly Large Telescope, but that hasn't gotten started yet. This is in Chile. This is a 39-meter diameter telescope, so 4 times the diameter of the Keck telescope. This should become operational at around 2030. And then we have 2 telescopes operated by the United States and its international partners. The first is the Giant Magellan Telescope, which takes multiple 8-meter mirrors, so the largest mirrors we can build out of a single piece of glass, brings them together into one giant 24-meter mirror aperture. And then the 30-meter telescope, which is notionally going to be sited on Mauna Kea, 30 meters across. And what's interesting is that right now we're looking at the way to combine these telescopes as a system called the US Extremely Large Telescope Program, so that US astronomers have giant telescopes on both the south, TMT is in the northern hemisphere, and GMT is in the southern hemisphere. And those two things working together present an immense opportunity to do the next generation of ground-based astronomy in concert with space, which is why I'm going to hand the baton off to my friend Tom Greene. So Tom, off to you. And I think you're still muted, Tom.
Very good. Mahalo, John. And I'd also like to give my thanks to the Hawaii Book and Music Festival. And everybody for being here. Aloha. And I would like to say a little bit about space telescopes. Some of this has already been said. So just like John, I have some experience both with ground and space-based telescopes, including on Mauna Kea. And as Roy said, I am a co-investigator on James Webb. I've been working on James Webb for 25 years. So it takes a while to do space telescopes. So first, I thought I'd start as to why we would put telescopes in space, because it's hard, as John said. Well, space is very stable. Like John said, we don't have blurring of the atmosphere. Also, the temperature is very stable. So that allows very high precision measurements that are impossible from Earth. You don't get temperature variations. It's a great environment for that. The sky is darker. That's a big deal with the Webb Space Telescope. It works at infrared wavelengths, which is heat radiation, and the telescope is very cold. So the sky is about 10,000 to 100,000 times darker than you would see at similar colors in the infrared than at Keck or other ground-based telescopes. And we can see more wavelengths or colors of light, as Roy said, that don't make it through the atmosphere. And one other thing is that we get more nighttime. We're not clouded out. And some of these telescopes, like Webb, has its own shade. It's not in orbit around the Earth, doesn't go through the whole day-night thing. And if you have a big shade blocking off the telescope from the sun, you can have nighttime all the time. So NASA realized this, and in the 90s, they put together a series of telescopes that were called the Great Observatories, and they worked at these different wavelengths. So as you know, the Hubble was still operating, so it's been flying for about 32 years. And Chandra is still working. This is X-rays. It was launched in the great year of 1999. A gamma ray observatory operated before that in the 90s. And the Spitzer was the infrared telescope before we had Webb, and it has finished its mission. It was about 50 times smaller in area, so it really didn't have the capabilities. So Roy did a great job showing the colors of light and what gets through the atmosphere. So our eyes only see this little bit of color. It's about twice, if you measure color in wavelength, the reddest red we can see is about twice the wavelength of the bluest blue we can see. But there's all this other stuff out here, and this is where a lot of things in space are emitting radiation. So it turns out that there's over half the amount of radiation at these long wavelengths than there is at these short wavelengths, and only part of the short wavelengths make it through the atmosphere. So the great observatories capitalize on this. The Hubble looking at visible, Webb is looking more into the infrared, and Spitzer looked even longer into the infrared. This I thought I'd show you some about stability in space. So it turns out most of the planets around other stars or exoplanets that we know about were discovered with this Kepler Space Telescope. And it looked at basically one area of the sky for about 3.5 years before it went off and did other things. And it looked for stars getting very slightly fainter when the planets moved in front of the stars. And after that, our next step is to use a similar technique to look for atmospheres, what's in the atmospheres around these planets. Now, it turns out it's hard to look for a lot of the same molecules that we have on Earth if we're not, if we are on Earth, because as we all know, there's a lot of carbon dioxide in Earth's atmosphere. And it's common in all the rocky planets in our solar system, except for Mercury, which is too hot. But Venus has a really broad carbon dioxide. It's high pressure. Mars has carbon dioxide, even though there's not a lot of atmosphere there. Earth does. Earth also has ozone because of oxygen. So if we want to look for this stuff, we can't do it from the Earth because these absorptions, these are what's called spectra, and where you see a dip here, that means the molecule is absorbing light. And that's actually sort of how global warming and climate change is happening, as the carbon dioxide is absorbing heat, and so the Earth can't get rid of it. But we can't look through it either to see carbon dioxide and other planets, so we have to go to space. You may have heard about the Webb Space Telescope. It launched on Christmas Day last year. We spent 6 months commissioning it, and now it's returning some pretty impressive science. It took a long time to build. Again, I started working on it in, I think I put my first proposal in 1997 on the first science team in 1998. It actually got approved and started to get built in 2002. It took 20 years. So this is sort of what it looked like when the telescope was being built. Like Keck, like John was saying, the mirrors are segmented. It has a lot fewer. It's smaller. It had to fit into the rocket. So actually this part of the mirror folds back, and you're seeing sort of like a folding table here. These segments fold back. And this is kind of a scale of a person. This is a little mirror that has to fold out to send the light back into where the instruments are. So we had to, so Webb has to be cold because that's part of the darker sky that we want, because it works in the infrared where a lot of objects produce emission. It had to be cold, so its own radiation wouldn't drown out the faint signals in the infrared from other objects. But we only know how to make mirrors warm, so we had to make them warm. And a lot of these, it had to be made out of a pretty exotic material. I'll go into that a little more later. It's called beryllium. It's like the fourth lightest element, because we just don't have the capability on rockets to launch a big glass mirror into space. Also, there's some issues with the rigidity of glass. So we had to polish these things warm and then test them cold into this test chamber. This is at this NASA facility in Alabama. And then they would measure the errors on the mirrors when it was cold, and then they'd have to touch them up warm again. So it was a pretty laborious process to do this cryogenic figuring. And yes, they are coated in gold, because gold is more reflective in the infrared than aluminum. This is just give you an idea of the scale of the testing. So one big thing you have to do with space telescopes that you don't have to do in the ground as much is test them. On the ground, you design them to work, you do some tests of subsystems, you put it all together, and then you try it all out. Well, we don't have the luxury of that in space, because it's really got to work the first time. Like John said, no uses serviceable parts inside for most of these things. So this is when we put the whole telescope. We refurbished this test chamber in Houston at the Space Center there. I think it cost about $100 million just to refurbish this chamber to be able to make it take down to really cold temperatures. This chamber was originally built for sort of roasting the Apollo command and service modules. So we finished the instruments. I remember in 2011, we finished testing the first one. They got delivered to this NASA facility in Maryland in 2012. And we started testing them there. We did 3 sets of cryogenic tests on the instruments, and then we put them on to the telescope. We tested them in this facility in Houston in 2017. And then everything got moved to Southern California and onto the spacecraft. So just the testing of this took almost 10 years. It was quite a lot of effort, and we spent months at it, 24 hours a day, 7 days a week. This is a little comparison between the Webb Space Telescope, or JWST, and Keck. So Keck is bigger, even though it started working 30 years earlier. As John said, first light, I think, for all the segments was in 1993. And it's got about 3 times the area. So that's about 3 times the amount of light gathering Keck does than Webb. This is sort of shows just how long it is. So Webb has to be, it's called faster, smaller F number, which means that it had to fold up to fit into the rocket. Keck can be a little bigger that way. It's a little easier to make optics that are a little longer focus. This shows that Webb works over a long range of wavelengths. So the eye can see out to about 0.7 microns in these units. That's a wavelength of really red light. And you can see about 30 times longer than what the eye can see with Webb. And Keck works out to 5, but again, it's very bright. You know, it's almost like when you're working in the infrared with Keck, it's almost like you are using a telescope made out of light bulbs and observing in the daytime. That's how it's been described. There are 18 segments on Webb, 36 on Keck. Now, this is a big deal here. Each segment on Webb is made out of this beryllium stuff. It weighs only 20 kilograms, about 50 pounds. 400 kilograms on Keck. So that's like 1,000 pounds. And we just can't build a space telescope like that. The mass of all of Webb is about 6 tons. That includes enough fuel for 20 years. Keck, just the rotating weight is 270 tons. You saw the size of those instruments that go up on there. And much more expensive if you amortize the construction costs over lifetimes. You know, it's at least like 10 times more expensive to do a big space telescope than a big ground telescope. So again, you know, we had to fold it up. It's not nearly as big as Keck, and we had to fold it up to fit it into one of the biggest rockets. And this is a picture from the launch on Christmas Day. And then it went through a kind of hair-raising sequence of unfolding. A lot of people put a lot of thought into this. There were like 340 mechanisms that had to work right. Unfortunately, they did. There's a lot of testing done. And this is what it looked like sort of when it was attached to the rocket, right when it was released. These arms come down. They're called pallet structures. They hold the sunshade. They get stretched out. This is very thin mylar. There are 5 layers of it. And this is what keeps the sun is always on one side and night is always on the other. And then the mirror wings had to come out. And it took about 2 weeks to do that. And then it took us about it had to cool down, and then it took us about 5 more months to check it all out. It took about a month just to align the telescope. It's 1 million miles away. It's not orbiting Earth. This is not drawn to scale, but it does show the sun, shows the Earth, and there are these gravitationally stable points that where you could put things in the Sun-Earth system. And this L2 point, is about 1 million miles from Earth. It's 4 times further than the Moon is. There's no way we're going there to fix anything. And if we did, just getting a spacecraft near there and any kind of contaminants would freeze out on the mirror because the telescope has to be cold. So it's great. You've seen the images, and you know I've gotten some data. It's fantastic. But why should we not? What are the drawbacks of putting telescopes in space? Well, I've already said that's time consuming and expensive, and it has to be very redundant testing and weird materials. I'm sorry about that. My mouse keeps on doing this. So also, because it takes so long, we can't update the technology. It's the technologies for Webb were frozen about 20 years ago. The electronics have to survive radiation, and they can't be upgraded in general. And the mission's over when we're out of fuel or something breaks. You know, again, can't fix it. Launch vehicles, rockets are limited size. So just to show you, what would your cell phone be like if it was was frozen when James Webb was, and it took 20 years. So if you just went down to buy a cell phone that was designed in the same era as Webb, this is what it would be. This is a Nokia phone from 2002 when the James Webb contracts were let, when it went through its preliminary design review. So just a last thing about what we learned about space telescopes. So you really only want to launch a telescope in space to take advantage of its environment, given the high cost, limitations, limited lifetimes. And we're never going to have telescopes in space that can do a lot of the science done from ground-based telescopes. First off, again, we're not going to have nearly as many. Like you see that one big space telescope we have is smaller than just one of the ones that are currently on Mauna Kea. And we won't be able to do this really high resolution work and with telescopes of the size that we can launch now, like this that won the Nobel Prize with Keck for this black hole science, measuring the masses of planets. We can find them in space, but we can't measure the masses. We need the ground for that. And also, there are many other ways that space telescopes and the ground work synergistically. So thank you. And I'll turn it back to Roy now.
Okay, thank you so much, John and Tom. And I think participants and Roger or the Book and Music Festival staff can correct me if I'm wrong, can post answers using the post questions. They might have answers too, but post questions into the Q&A using the Q&A button at the bottom of your Zoom screen. So please go ahead and do that, and then we'll pick out ones that we can answer. And while we wait for that to happen, I want to say that we talked about why we have different kinds of telescopes and what things ground and space-based telescopes can do. But I'd like to ask John and Tom to address how ground and space-based telescopes actually aren't necessarily competing with each other, but are part of an ecosystem of telescopes that work together to deliver science and answers to questions about the universe.
Do you want to start with that, John?
Sure. I think what I'll do is I'll give a pretty famous example for those who know and love astronomy, which is there's this wonderful image taken by the Hubble Space Telescope, which is called the Hubble Deep Field. It's at least until Webb launched, it was the deepest look into space we've ever taken with any telescope. And in a spot on the sky, the size of Roosevelt's eye, if you held a dime at arm's length, there are over 10,000 galaxies seen by this image. So this was really one of the most powerful images in terms of the impact on our understanding of the universe that had been taken, but it lacked context, right? You could see all of these beautiful galaxies in it, but we didn't know, at least to any sort of precision, how far away those galaxies were. And that's where another telescope came in, and that was the Keck telescope, that it and other ground-based telescopes went and found the distances to each one of those galaxies, or a significant enough subset of them, to really learn about those things. But that was an example where both of the telescopes were absolutely essential. You couldn't take that image with Keck. You could not. You just couldn't get past the blurring of the atmosphere and the optical wavelengths. But Hubble could not get the distances to those things without spending the entirety of the rest of its mission trying to go after it. And so that's a really good example of why the two need each other. And we're starting to already see this with Webb. And, Tom, I'll pass it to you on sort of like, what are the fun things that we're seeing with Webb that we know we're going to have to do with ground and vice versa?
Well, just in the bigger picture, we need to know where to point Webb. The ground has been excellent for that, for finding interesting objects. There are these telescopes, and some of them are quite small, doing big surveys of the sky, finding all sorts of interesting objects there. And so it really gives the big picture that we can then zoom in on interesting objects with Webb. One area that is something I work in is planets around other stars. So we've had various all-sky surveys in space and the ground, but in the ground in particular, found a lot of the best planets that do from this transit technique, big planets. And the ground also measured their masses with other instruments. And with Webb, we can then characterize, we go to one of these planets that we already know about from the ground, and we know that it transits, we know how big it is, we know how it transits the star, we know the mass, and then we'll measure the atmosphere. We need all that information together to really kind of understand what's going on in the atmosphere of that planet. And particularly, like some big questions I think we all have, is what we see in the atmosphere, those chemicals, how similar is it to Earth? And also, is it natural ratios of these different chemicals, these molecules, or are they out of balance due to life? So, and we need all that information from these different methods to get to figure this out. It's a hard, there are a lot of hard problems in astronomy that take information in many forms.
And just for our viewers, I'll just show you what the Hubble Deep Field looks like. So there it is. And you can see all these tiny dots and colorful objects. And just about everything in this image is a galaxy filled with hundreds of millions of stars. One individual star here with these spikes due to the telescope structure. There's a handful of stars in this image. And our organizer asked, how do we choose our targets? Well, for instance, the Hubble Deep Field region was chosen to be devoid of any bright stars so that we could see all of these faint, distant objects. And everything in this picture, I don't know what comes across on Zoom, but every teeny dot of light is a galaxy. So like John said, even though this is a teeny, teeny, tiny portion of the sky, it's got thousands and thousands of objects. And then if we want to measure the properties of one of these galaxies, we need to take a spectrum of it. And that takes a big telescope because we're spreading the light out. So that's an example of how these work in synergy. And just to throw another one out there, that's kind of I think, an interesting back and forth of space and ground. We probably all saw the DART mission recently, where we hit one asteroid orbiting another asteroid with a spacecraft. So we sent a spacecraft to take pictures of an asteroid and then hit it with another spacecraft. We had a CubeSat taking pictures of the impact. And then we had ground-based telescopes like our Atlas system that saw the plume that happened after the impact and that are measuring the orbit. We had Hubble and James Webb looking at the material coming off after the impact. So we had spacecraft hitting asteroids being watched by other spacecraft, being watched by ground-based telescopes, and followed up by more spacecraft. So really, it's sort of bringing all the tools we have to bear on a question. None of them does it all. It really is like having a toolbox, right? If you had your toolbox with only hammers, you wouldn't get very far.
I noticed there's some questions in the chat.
Could I attempt to answer Natalia's one, Roy, and then if you want to join in as well?
Yeah, and I'll just say, to summarize for those who aren't looking at the Q&A, someone asked about the timeline of designing and testing telescopes, and then what happens after a telescope is past its useful lifetime.
Yeah. So for ground-based telescopes, particularly those in which are built in places of significant importance to many people, whether or not that's cultural, historical, archaeological, ecological, astronomical. One such place certainly is Mauna Kea, which is extremely, extremely important to many, many, many people in fundamental, deep ways. Natalia is asking, is properly dismantling and disposing and or repurposing telescopes an important part of the process? The answer is yes. All the telescopes on Mauna Kea have written in as part of their lease terms is that when they decommission the site that they are on, if there is no upgrade to the telescope or repurposing of that site must be returned to its natural state. And we're witnessing that process happen right now with the Keck Submillimeter Observatory, which is actively undergoing decommissioning right now. And in 2 years' time, when you go past that spot on Mauna Kea, you will not know that a telescope was there. And I think that's a critically important part of the commitment that telescopes that operate on Mauna Kea and in other places, and most of the astronomical sites in the world are also revered sites by many cultures, in part because they're such special places to look at the sky. And so, we do have a commitment as astronomers to work responsibly and be as sensitive as possible and as collaboratively as possible to keep those sites well maintained, and ideally when the scientific utility of those things is done to restore those sites back to their original state. And so, I believe all the sites on telescopes on Mauna Kea are committed to doing that.
And maybe, Tom, you can mention, space is an important consideration right now. Just today, they launched some more Starlink satellites. We've had issues of satellites colliding with each other or being intentionally destroyed. So the space environment itself is also very important to humanity. We all share the same sky. What's the situation for space telescopes? James Webb is in an orbit that's far away from Earth, but how do we handle telescopes in low Earth orbit, for instance?
Well, now when we propose new telescopes, we have to bring them down. Hubble will be brought down too. So this is something within a few years of the end of the operation. We're going to deorbit them. Most of them are small enough, they'll burn up in the atmosphere. Some of them will have some parts that'll make it through, and they'll be, they will hit the surface of the Earth. But most of the telescopes will be destroyed when they re-enter the atmosphere, and that is, a big part. Space's low Earth orbit is getting really crowded, and there's several times more more satellites now than there were 15 years ago.
And you're very welcome, Natalia. We have a question here from Roger about how land use conflicts that we're seeing all over, whether it's in the Canary Islands or here in Mauna Kea or on mountains on the mainland, how that factors in as a constraint on ground-based telescopes and how we're handling that and think about handling it in the future. So I'll let John answer that question, but I did want to address it first, if that's okay, John, which is, I do think that this is something that has come up since the advent of ground-based telescopes. So for instance, when Palomar was built or Mount Wilson, this was not such an issue. And the fact that indigenous cultures now actually have more of a say and are being more assertive about their position is actually an important and a positive development. And it's really forced astronomers to think about this much more deeply than we would have done half a century or a century ago. And so I think John knows more details about how that's being handled locally and maybe has a broader perspective of how it's handled nationally.
Well, Roy, I mean, you started with exactly what I wanted to say, which is historically, this has not been a big part of the calculus for ground-based astronomy. But really, if I take, for example, Mauna Kea, as Native Hawaiian agency is rising and is being acknowledged, and Native Hawaiian perspectives are being acknowledged at a cultural level, at a legal level, at a variety of levels. And it's really important that that perspective and that agency be a fundamental part of the conversation of how we operate across the Hawaiian Islands, not just Mauna Kea and astronomy. And that's becoming much more forward and prevalent in the discussion for land use, not just astronomy, but just land use in general. But for these places of significant indigenous cultural importance, it really is the responsibility of astronomy to be the best possible partner that we can. And I think there's been very, very positive developments in recent years on that. I believe that the University of Hawaii has been a very good steward of Mauna Kea in terms of archaeological monitoring, ecological monitoring, et cetera. And we're beginning to go forward in a new management paradigm of mutual stewardship, where astronomy and other voices are really centered on Mauna Kea, and then how we start with Mauna Kea and then branch that out to astronomy. And it's that change, that acknowledgement, that intent of acknowledging that the Mauna is at the center of this, that's really the important change in the dialogue. And I'm quite positive that astronomy can continue to flourish on Mauna Kea, but be a good partner there. Like I said, the university has set the stage for us to be the best possible partners as we move forward into the next decade. And so it's really, I think, a time of, it's oftentimes we focus on the uncertainty of it, but I actually think there's a time to have immense opportunity to really work collectively, collaboratively on great stewardship of Mauna Kea and a flourishing astronomy that's community responsive and is really a good partner. I think it's partnership, it's community, it's all of those things, and really this is a new perspective that's only come out really in the last couple of decades and is a critical part to our success in future.
If I could add a word or two, I noticed the question also asked about Kitt Peak. Now that's interesting. So Kitt Peak is a collection of telescopes in Arizona, outside of Tucson, Arizona, that predates Mauna Kea, I guess, by about 10 years in terms of exploration. The 1950s, people were starting to test it as a site. There were discussions with the Tohono O'odham people that revere Kitt Peak and have it as their home. They were also came to Tucson, looked through some telescopes, had some discussions, and I wasn't there at the time, but there was at least some welcoming of at least the first facilities on Kitt Peak. So people were able to work it out between themselves at sites, and realizing that sites are important to people, and also knowledge is important. So hopefully the future will work that way also.
Then we have a question about, is it necessary for the telescopes to have such a high physical profile? And that is actually, the answer is sort of yes. If you wanted to dig deeper, you'd be removing more of the Mauna. But in terms of telescope design, the design of telescopes has come a long way. So the Palomar Observatory, which houses a 5-meter telescope, the dome is the same size as roughly as the Keck 10-meter telescope dome. So the enclosure of Keck is the same size, even though the mirror is twice as big across. And in fact, the TMT, the 30-meter telescope dome, is only fractionally taller as a structure than the Subaru telescope dome. The Subaru telescope dome houses an 8-meter telescope, and we're going to put a 30-meter telescope in a dome that's about the same size. And that was a huge part of the TMT design, was to make it very fast. Tom mentioned that space telescopes have to be very fast. Large telescopes have to be very fast also, because otherwise you get an enormous dome. Plus the TMT site is lower on the Mauna. So I think that kind of between technology and the attempts to reduce the size of the structures, we've done pretty much what we can. I mean, the TMT is basically wedged inside its dome. The dome is only marginally bigger than the size of the mirror. So like the European overwhelmingly large telescope, which would have been 100 meters across, I don't think that would have even been inside a dome necessarily, or you're talking about going to sort of football stadium style buildings. So, but you definitely don't want to dig more into the mountain and do more damage to the mountain. That's an absolute no-no. And John's nodding his head and he can say more about that.
No, I completely agree. I think the other consideration is that the larger the dome you make in principle, the more turbulence you're introducing in the air near the telescope. It's heavily a function of the shape of the dome, but just the physical imprint of it means air is slamming into it and becoming turbulent. So, you know, there's very good reasons to want to minimize the visible impact of any telescope, particularly on Mauna Kea. But there's also good, you know, astronomical reasons to do it as well, which have to do with turbulent flow over.
Okay. I wanted to ask a question to the panelists. We've talked about the telescopes today, and we've mentioned some upcoming ones like the Rubin Observatory in Chile and maybe the ELTs. But what do you see as the future of both ground and space-based observatories in terms of technology and size? Obviously, we can only really see what we know with today's technology, but what do you think the next, I don't know, 5 decades or so might hold for us?
Well, I can start off a little bit with space. So every 10 years or so, the astronomers get together in the US and decide where the big scientific interesting questions are, where the technology is, what can be done. So what's been sort of forecast for space is building something about the size of Webb for big telescopes, but to work in visible light and to be very precise, and also be able to have a device that can blot out a bright star and be able to see a faint planet next to it. With that, we need that kind of technology to see Earth-like planets around stars and measure their atmospheres. So the kind of technique, the transits that Webb uses, will never get there. So that is going to take, we don't think that's going to launch until the 2040s because it's going to take 10 years of technology development. It's going to cost well over $10 billion. I think the estimates of like 10 or $11 billion are probably way too low. It's going to be really hard to test and all that. And again, we're going to be limited by the size of the launch vehicles, be limited by the size, you know, of people's ability to pay and whatnot. Also, a survey telescope in space that'll be very complementary to the Rubin that John showed that is coming. It's going to work more in infrared wavelengths, whereas Rubin works in visible wavelengths. Its camera won't have as many pixels, but it's going to have 100 times the field in one exposure that Hubble does. So that's going to be quite a powerful thing. And also, we're building things to follow up these survey telescopes. And a lot of these are very specialized. They're smaller. And we're getting into also trying to build space telescopes for not much money. I'm on one. It's a class called Pioneers mission. It's called Pandora, where we've got a 0.5-meter mirror, and it's going to hopefully launch and cost only about $20 million. It's about the cost of one of the Keck instruments, you know, that goes behind the telescope. It'll be very specialized, looking at some exoplanet things. So that's a little bit of what's coming in space.
I'm actually going to be a little bit more optimistic than Tom is for space, if only because I worked on one of the mission concepts. I think we can go a little bit bigger, but without dramatically blowing up the cost. But Roy, on 50-year timescales, I actually think we're going to start to consider in-space assembly of telescopes. That is to go to significantly larger sizes, because we may be able, with larger rockets, bring up pallets of things and assemble them in space. But that requires a totally different flavor of technology investment than what we're doing today. It requires robotic investments in human space flight that we haven't been doing on Mars. For the ground, I actually think we're going to stop at around 50 meters for single optical IR telescopes. The big advancements will be the technology and the instruments that we put in them. Special detectors that have no read noise, or special detectors that can do spectrums on individual pixels. This star nulling technology. For telescopes at different wavelengths on the ground, though, like radio telescopes, we're going to build bigger and bigger interferometers, huge telescopes that cover, that have a mirror that's almost the size of the Earth, and sometimes the size of the Earth's orbit around the sun. But I think primarily the big development for ground-based telescopes in the next 50 years is moving towards even more powerful instrumentation and towards adaptive optics that can start to work at visible wavelengths, so that we can have the power of a space telescope sometimes on the ground. But I think, in my closing thought is, I don't think the synergy, the play between those two things, ground and space, will ever cease being really important. I think the science will continue to demand that we have both flavors.
That's a great closing statement. And I'll add to that as Roger comes on, that let's remember that for every space-based telescope, there's a factor of 10 or more ground-based telescopes. So to just support the astronomy community and the questions that we're trying to answer, we cannot ever have enough space telescopes for the money that we have available.
Well, thank you very much indeed. That was absolutely fascinating and quite an education in just 1 hour. And Roy, just terrific moderating as usual. So with great thanks and aloha, I bid you good evening.
Thanks, Roger. Will you send us the link of the final recording?
Yes.
Aloha, mahalo.
Aloha, everyone. That was an excellent conversation. Thank you.
Aloha. Mahalo.
Mahalo.